You've seen them everywhere, right? These incredible images, poems, even music, all made by AI. It honestly feels a little bit like magic, but it's not. It's a technology called generative AI, and in this explainer, we are going to pull back the curtain and show you exactly how it works.
Okay, so just look at this. An astronaut on a horse. The detail is amazing, it's super compelling, and it is 100% fake. An AI made this from just a few words of text. This scene never ever happened. So how in the world does a computer imagine something like this? That is the exact question we're going to answer.
The technology behind that crazy image is something called a generative model. And really, the key idea is right there in the name. You see, unlike most AI that just analyzes the world, these models are designed to add to it.
So what does that really mean? Well, these models are trained on gigantic data sets. We're talking millions of photos. But here's the thing. They don't just memorize them. They actually learn the underlying patterns and rules, like what a sky generally looks like, or the texture of fur, or how light and shadow work. They learn it so deeply that they can create brand new images that are completely original, but still follow all those rules they learned.
You know, this ability to create is what really separates generative AI from the kind of AI we might be more used to. And to really get what makes it so special, we need to look at the two sides of the AI coin: learning versus creating.
So on one side, you have discriminative models. Their job is pretty straightforward. They classify things. You show it a picture, and it answers a simple question, like, does this contain a cat? But on the other side, you've got generative models. They're the artists. You don't ask it if there's a cat, you tell it, create an image of a cat. One's a judge, the other's a creator. Big difference. Okay, so how do they actually do this creating? Well, one of the first really big breakthroughs is best explained with this brilliant analogy. Think of it like a high-stakes cat-and-mouse game between an art forger and a detective. The technical name for this is a generative adversarial network, or GAN for short. This idea really kicked things into high gear back in 2014, and that word, adversarial, is the absolute key, as you're about to see.
First up, let's meet the forger. In the AI world, this is called the generator. Its entire purpose is to take random static, literally digital noise, and try to turn it into a convincing fake, something that looks just like a real photo.
And of course, trying to catch the forger is the detective, or what we call the discriminator. It gets shown a whole mix of images. Some are real photos from the training data, and some are fakes from the forger. Its only job is to tell them apart, to just say real or fake.
And this is where it gets so clever. You can see here how they're locked in this constant competition. The generator creates a fake, the discriminator tries to spot it. Every single time the generator gets caught, it learns and tries to make a better fake next time. But every time it succeeds, the discriminator has to get smarter to catch the next one. They both level up, millions of times, until the fakes are so good they're basically indistinguishable from the real thing.
GANs were a huge breakthrough, no doubt. But a newer, and in many ways more powerful, technique is behind a lot of the jaw-dropping images you see today: diffusion models. So, if GANs are a forger and a detective, think of diffusion as a sculptor who sees a statue hidden inside a block of marble.
The core idea here is absolutely fascinating. Instead of starting with nothing, diffusion models actually start with a perfect image. They systematically destroy it by adding noise step by step. And then, and this is the crucial part, they train an AI to learn how to perfectly reverse that whole process.
The training process is a little counterintuitive. You start with a nice, clear image, and then you deliberately destroy it. You just keep adding noise, step by step, until it's nothing but static. The entire point is to train the AI to be a master at reversing this process, to learn exactly how to remove the noise at every single stage. Then, once it's an expert at cleaning up noisy images, you can perform the magic trick. You give it a block of pure noise and just tell it to clean it up. It then sculpts a brand new, totally coherent image right out of that static.
So we have these really powerful concepts. Now let's see how a state-of-the-art diffusion model actually puts these ideas to work to turn a simple text prompt into a picture.
This diagram shows the entire journey. It starts with our text prompt way over on the left and ends with that final beautiful image on the right. Now, it might look complex, but we can actually break it down into 3 key stages: encoding the text, the diffusion process itself right in the middle, and then decoding the result. So, those 3 components are the text encoder, which has to read our prompt, the diffusion model, which does all the creative heavy lifting, and the decoder, which assembles the final picture for us. First up, the text encoder. A computer has no idea what astronaut or horse means. So this component's job is to act as a translator. It takes our text prompt and turns it into a special mathematical code, a set of numbers that represents the meaning and the concepts in our sentence. This code basically becomes the instruction manual for the next step.
Next, the diffusion model itself gets to work. It takes a patch of random noise and, guided by those numerical instructions from the text encoder, it begins that whole denoising process we talked about. Over many, many steps, it shapes that static into a compressed, abstract representation of our astronaut and horse. It's not a picture yet, but it's a rich summary of all the information needed to make one. We call this data-rich blueprint a latent patch.
And finally, the decoder steps in. Think of it like developing film in a dark room. It takes that compressed, latent patch, that blueprint, and it blows it up, translating all that abstract data into the actual pixels, colors, and details that form the final, high-resolution image that we get to see.
So, we've gone from a simple idea all the way to a complex image. But what does this technology mean beyond just making cool pictures? This is where it gets really, really interesting.
And here's the crucial point. This core idea, learning the patterns in data to create new versions, it applies to almost anything, not just images. The same techniques can learn the patterns of music to compose a symphony, or learn the patterns of human language to power a chatbot. It can generate voices, write computer code, and even create 3D models for virtual worlds.
And that really brings us to the big takeaway. We're entering an era where the barrier to creation is no longer technical skill, but pure imagination. Which leaves us with a fascinating final thought. If anyone can create anything they can describe, what will we choose to create?